Hi, welcome to Dissolved Chemistry. Let us continue our discussion on this chemical equilibrium. In the previous video, we have discussed regarding heterogeneous equilibria. Okay, and we have discussed about units of equilibrium constant and important features of equilibrium constant. Now, in the present video, we will discuss regarding the applications of a equilibrium constant. Okay. Applications of equilibrium constant. Okay. The first important application of this equilibrium constant is in the prediction of extent of reaction. Okay. Now, the numerical value of equilibrium constant for a given reaction will give the information regarding to what extent the reaction has occurred. How? Let us see that. Okay. Say for example, A plus B combines to give C plus D. Right? Then your equilibrium constant equation for this reaction, how we will write? So Kc is equal to C into D divided by A into B. Okay. So molar concentration of the products divided by molar concentration of the reactants. Okay, when you keenly observe the equilibrium constant equation for a given reaction, you see that the products are appearing in the numerator and reactants are appearing in the denominator. As they are appearing in the numerator means they are directly proportional. The molar concentration of the products is directly proportional to equilibrium constant, whereas molar concentration of the reactants are inversely proportional. It means the higher the value of equilibrium constant, the reaction, the products are going to predominate at equilibrium with respect to the reactants. Okay, so therefore we will fix the values. Okay, above which if it is there, then we call it as what reaction is going to be almost to the completion. That value we will see. So first one is the condition is that if the equilibrium constant value is greater than 10 to the power 3, then we say that the reaction has occurred to almost completion, and here products will predominate over reactants. Okay, so when the Kc value, equilibrium constant Kc value is greater than 10 to the power 3, then it will be greater. When the concentration of the products are high, then its value will be high because it is directly related to the products and inversely related to the reactants as they appear in the denominator and products appear in the numerator. Okay, so for example, we will take the combination of H2 plus half O2 to give, or we can take like this, 2 moles of H2 plus 1 mole of O2 to give H2O reversibly. Okay, its equilibrium constant will be Kc is equal to 2.4 into 10 to the power 47. Okay, you can see that it is almost on the verge of the completion. Okay, and it means at equilibrium the concentration of H2 and O2 will be very less. And one point you should make note of prior to going for the next example, that the equilibrium constant value never speaks about the rate of the reaction. Okay, it will not give any information. So with what rate, how much time it has taken to attain this equilibrium constant or to attain the equilibrium. So we are not bothered about that, or it will not tell anything about that. only at equilibrium, the equilibrium constant value, okay, so this value indicates that, okay, so that the reaction has almost is on the verge of completion, hence it has attained an equilibrium at that moment, and we got this Kc value as this. Next, one example we will take: H2 gas combines with Cl2 gas, okay, to give 2 moles of HCl gas. The equilibrium constant value for that will be 4.0 into 10 to the power 28. Okay, so this is the equilibrium constant for HCl, formation of the HCl. So all these are having values, equilibrium constant value greater than 10 to the power 3. So therefore, they are on the almost verge of the completion, or products are going to predominate at equilibrium with respect to the reactants. Okay. Then next we will see second condition we will take. When the equilibrium constant value is less than 10 to the power minus 3, okay, indicates that the hardly the reaction has occurred, it says, okay, prior to attaining an equilibrium, very small extent of the reactants have been converted into product. Okay, so therefore at equilibrium, reactants concentration predominates over product concentration. Okay, so when the value of Kc is less than 10 to the power minus 3, so then your reactant concentration will be always predominating over the products. For example, you can consider decomposition of water we will take, okay, to give 2 moles of water to give H2 plus 2H2 plus O2 gas. Okay, your equilibrium constant value will be 4.6 into 10 to the power minus 47. Okay, so this is the Kc value, which indicates that at equilibrium, the concentration of reactant is too high, or it is going to predominate over the concentration of the what products, that is H2 and O2. Okay, so that is how we can indicate from this equilibrium constant value. Okay, okay, when the equilibrium value lies between the range of 10 to the power minus 3 to 10 to the power 3, then we say that the reaction at the time of attaining has occurred to the appreciable amount where both reactants and products are present in the appreciable. So for example, you can take combination of H2 plus I2 reversibly to give 2HI. The equilibrium constant Kc value is 57.0 at 700 Kelvin temperature. Temperature also plays very important role. At what temperature that equilibrium constant we got with. Okay, so it indicates what it lies between what these two values. So therefore it is what it occurring at an appreciable amount, we say. Average reaction will happen, means like 30, 40, 60% of the reactant might have been converted into products, we can say. Okay, then we will summarize all these three. Okay, so this you take it as what reaction axis. So here you call it as product predominates, and here reactants predominates. So here we will write 10 to the power minus 3, here we will write 1, and here we will write 10 to the power 3. So greater than this, what you will be finding? The product is going to predominate, and less than this, reactants will predominate. So this is your Kc value. Okay, all these three are what? Kc values. Now in between these two values, the concentration of both reactants and products are present in appreciable amount we can say. Okay, so that is how we can predict from the equilibrium constant value that either the reaction has occurred to what extent, or either product is dominating or reactant is dominating, that we can assess. Okay, the second important application of this equilibrium constant is in the predicting the direction of the reaction at any instant. Okay, so how we can predict this one? The direction of the reaction. See here, once the reaction commences, okay, say for example, we will take this is the reaction which is progressing, right? I have taken A plus B combining to give C plus D, right? So assume that its equilibrium constant Kc for this given reaction is, say for example, 10 to the power 3 we will consider. Okay, for example, 10 to the power 3, right? So now at any instant when you start the reaction, here we are starting the reaction, okay, so your reaction concentration will be very high initially and product will be very less, and at any instant when we check the ratio of a concentration of the product to the concentration of the reactants, that we call it as what? Reaction coefficient we call. Okay, the product of molar concentration of the products to the product of molar concentration of the reactants at any instant of the time, okay, during the reaction, okay, is called as what? Reaction coefficient, and it is also given by the same formula. Q is equal to C into D raised to D divided by A into B. Okay, but it is not at equilibrium, it is at what? At any instant during the reaction we call. Any instant during the reaction. Okay, and how we can make this as tool for identifying that in which direction the reaction is heading. Okay, so that we can see that if this Q value, okay, for a given reaction, if it is less than the equilibrium constant, Q is less than equilibrium constant Kc, then always remember the reaction will be in the forward direction. Reaction is progressing in the forward direction we call. Okay, if the Q value is greater equal to Kc, then we say that Q is equal to Kc, then the reaction is at equilibrium. Already reaction has attained an equilibrium, we can say. Now suppose if the Q value is greater than Kc value, then the reaction will be in the backward direction or reverse direction. Okay, so this is how we can tell that one. Okay, if it is greater than this 10 to the power this, okay, so Kc value, if it is high, a Q value is greater than Kc, so then what happens? It will be in the backward direction because it has to attain our equilibrium constant is 10 to the power 3. So therefore 10 to the power 4 is there, for example, concentration. Okay, then automatically it is Q value. Okay, at any instant of time during the reaction we said. So if it is high means what does it indicate? Q value. So therefore still reaction has scope to go in the backward direction. If it is, say for example, 10 to the power 2 Q value, so therefore still it has not attained an equilibrium concentration, so therefore it will be having scope to go in the forward direction. I hope you have understood. This is how we can determine the direction of the reaction at any instant okay, during the reaction. Okay. The third application is in the calculation of equilibrium concentration. Okay. Suppose if we know the initial concentration of the reactants and if you know the equilibrium constant value for a given reaction, then we can calculate what are the equilibrium concentration of the reactants and products are there. Okay. So that we can do, there are steps are there that we are going to follow to calculate that. Okay, and similarly, if we know the equilibrium concentration and initial concentration of the reactants, we can calculate the equilibrium constant. Okay, so that part of calculation and all that we will discuss in detail when we go for solving the numericals on this particular aspect. Okay, next important aspect is relationship between Gibbs free energy, then reaction coefficient and equilibrium constant. At a delta G value, if it is negative, okay, is negative, then we said that the process is said to be spontaneous. Okay, just try to remember this one. So this already we have discussed in thermodynamics video. If you want to know more, you can go to that particular video. Okay, then delta G value, if it is equal to 0, then at equilibrium we have said. Okay, and if the delta G value is positive, then we said that it is non-spontaneous in that particular direction. Okay, non-spontaneous, right? So these aspects we have discussed in thermodynamics, and now we will go to relate with this Gibbs free energy and reaction coefficient Q and equilibrium constant. Now, when the reaction is progressing, okay, then we give delta G as delta G is equal to delta G naught plus RT ln Q we call. Okay, when the reaction is still progressing, still it has not attained an equilibrium, then delta G is given as delta G is equal to delta G naught RT ln Q. Okay, where delta G naught is standard Gibbs free energy change for a given reaction, and delta G is Gibbs free energy, R is gas constant, T and constant temperature, Q is your reaction coefficient. Okay, now if it attains an equilibrium, okay, at equilibrium, right, so that is your delta G is equal to 0 and your Q is equal to Kc. Okay, so therefore if we substitute this in equation, what we will get, 0 is equal to delta G naught plus RT ln Kc. Okay, so or we can call it as what, delta G naught is equal to minus RT ln Kc we call, right? Then we know that ln Kc is equal to minus delta G naught by RT, or we can say that Kc is equal to e to the power minus delta G naught by RT. Okay, so this is how the equilibrium constant is related with Gibbs free energy. Okay, now when the value, okay, we will see that how the reaction, either it is in the forward direction or backward direction based on the value of standard Gibbs free energy. Okay, so that we will see. Okay, we will see that how with this case is related with our delta G. So delta G naught by RT. Okay. So now if delta G value is negative, okay, so then the Kc value will be delta If delta G naught value is negative, meaning is what? It is less than 0. Okay, negative means, so overall these terms become positive. So therefore your Kc will be greater than 1. When the Kc value is greater than 1, it implies that the reaction occurs in forward direction such that products are going to predominate or going to predominate over the reactants. Okay. Then second important point is below 0 meaning is what? Negative. Negative into negative means positive. Positive means this becomes positive. So therefore Kc will be greater than 1. So now if the delta G naught value is greater than 1, means that is if it is positive value. So then what happens? Your Kc will be what? Less than 1. When it is less than 1, then the reaction will be occurring in the what? Opposite direction or reverse direction. Hence your reactants will be more predominant over the products that it implies. In the upcoming video, we will discuss regarding various factors affecting the equilibrium, and important aspect, that is Le Chatelier principle, also we are going to discuss. Okay, thank you for watching.